sklearn, linear model, LassoLars. Description. The LassoLars model is a linear regression model that utilizes the least angle regression LARS algorithm to solve the lasso problem. The algorithm is similar to forward stepwise regression but with an important difference: it finds a whole path of coefficients as the lasso penalty parameter changes. This is a useful approach as it is often preferred to estimate an entire path of coefficients instead of a single coefficient. This allows for better visualization and analysis of the model's behavior. Inputs: X a 2D array of independent variables. Each row represents an observation, and each column represents a feature. Y a 1D array of dependent variables. Outputs: Coa 1D array of coefficients of the linear model. Intercept: the intercept of the linear model. Steps: the LARS algorithm starts by selecting the feature that is most correlated with the target variable. It then moves along a direction that is equiangular between the selected feature and the next most correlated feature. It continues to move along this direction until it hits the constraint imposed by the lasso penalty. It then selects the next most correlated feature and repeats the process. Metrics: R-squared, a measure of how well the model fits the data. Mean squared error, MSE, a measure of the average squared error between the model's predictions and the actual values. Mean absolute error, MA, a measure of the average absolute error between the model's predictions and the actual values. Visualization plots. Coefficient path plot, a plot of the coefficients as a function of the lasso penalty. Residual plot, a plot of the residuals, the difference between the model's predictions and actual values against the predicted values. Fine-tune parameters. Alpha, the lasso penalty parameter. A larger value of alpha will lead to more coefficients being set to 0. Fit intercept, whether to fit an intercept to the model. Normalize, whether to normalize the features. APES, the stopping criterion for the LARS algorithm. Uncertainty methods. Bootstrap, resampling the data with replacement and fitting the model to each resampled dataset. The distribution of the coefficients can then be used to estimate the uncertainty. Cross-validation, dividing the data into multiple folds and fitting the model to each fold. The performance of the model can then be averaged across the folds to estimate the uncertainty. Challenges and fixes. Challenge 1: the LARS algorithm can be computationally expensive for large datasets. Sample use case that resulted in Challenge 1: fitting a LassoLars model to a dataset with millions of rows and thousands of columns. Fixes to Challenge 1. Use a smaller subset of the data for training. Use a more efficient implementation of the LARS algorithm. Use a different regularization method, such as elastic net. Challenge 2: the LARS algorithm can be sensitive to the choice of the lasso penalty parameter. Sample use case that resulted in Challenge 2: selecting a lasso penalty parameter that is too small can lead to overfitting. Selecting a lasso penalty parameter that is too large can lead to underfitting. Fixes to Challenge 2. Use cross-validation to select the optimal lasso penalty parameter. Use a grid search to find the best lasso penalty parameter. Use a Bayesian optimization algorithm to find the best lasso penalty parameter.